Welcome everybody to the afternoon session. If it is afternoon where you are, I don't know. It is afternoon here. And what better way to kick off the session than James East from Western Sydney University. He's going to be talking about some Ehresmann theory things to do with semigroups. Over to you, James.
Thanks, John. Thanks to the organisers for this opportunity. This is the closest I've come to visiting Perth. So it's like one of the previous speakers said, it's a pity we can't all be together, but well, close as I've gotten so far. So this is a talk about essentially two strands of semigroup theory. One is Ehresmann monoids on the one hand, and one is partition monoids. And this is about a paper written with my collaborator, Bob Gray, just come out this year. It kind of connects these two ideas. The Ehresmann stuff is fairly new for me. And from my perspective, it sort of is a new way to think about partition monoids, which I've thought about a lot. And hopefully the idea is that, well, if you're interested in either of these things, then it'll kind of make the other perhaps seem interesting as well. So this is Bob with some good advice on his shirt. And for the purposes of this talk, I will just be slightly updating that a little bit. You don't get to listen to Bob today, just me. So what's the idea? Well, I'm going to start talking about inverse monoids, which are hopefully familiar to a few of us. They've been at least implicitly mentioned a few times during the conference so far. So I'll be talking just about monoids today, basically a semigroup, so an associative operation on a set, and it has an identity, just to keep things a little bit simpler. And what is an inverse monoid? Well, it's kind of like, it's part way between a monoid becoming a group. So these things have inverses, but they're not sort of group inverses. So an inverse of an element X is an element A that satisfy these equations. So it's kind of like you undo X a little bit. A colleague of mine described this once as saying, well, in groups, it's sort of unrealistic because, you know, if you drop an egg, you break an egg, you can't put it back together again, but you can put it back where you found it. And that's sort of what a semigroup inverse is. I think that only semi makes sense, but anyway. So an inverse monoid is a monoid where every element has a unique inverse. All right, and when that's the case, well, the inverse of an element is unique, so we can give it a special notation. X inverse is the usual one. And so what that means is that X inverse is an inverse of X in the sense just described, so these equations hold. And for example, if you multiply the left one of these on the right by X inverse, you see that X inverse is an idempotent. But unlike the group case, these don't have to equal the identity of the monoid. They're some other idempotent, perhaps. So the most obvious example is a group where the inverse is just the ordinary group inverse. And at the other extreme, we have semilattices where we just have a bunch of idempotents that happen to commute, and the inverse of any element there is itself. So inverse monoids have many different ways to define them, or they have many equivalent characterizations. One of the most important is this one, which in fact goes back to Roger Penrose, who was a promising semigroup theorist before he became a physicist. Not everyone knows that, but it's true. And it turns out M is inverse if and only if it's regular, meaning every element has at least one inverse, and the idempotents commute. So somehow the commutativity of idempotents imply uniqueness of inverses, and this is a really non-trivial characterization. Another way to describe inverse monoids is equationally. So we have a unary operation sending an element to its inverse. You can check that it satisfies these laws. Again, this is not trivial. And conversely, any semigroup with a unary operation satisfying these laws turns out to be inverse. You can describe inverse semigroups as inverse monoids as monoids having certain properties concerning Green's relations, which I'll talk a little bit about later on, so I'll just sort of gloss over these for now. And you can think of these more concretely, just like we can think of groups as permutation groups. You can think of inverse monoids as monoids of partial bijections this would have had a word like suitably represented if I had a bit more space, but you can think of them as monoids of partial bijections or block bijections, which I'll mention shortly. That's not as familiar a concept. And in fact, you can restrict these ideas to say that the partial bijections have to preserve just about anything. So I think we saw this in Alejandra's talk the other day, something to do with C-star algebras. A lot of people are interested in inverse monoids. You can basically take any of those characterizations and kind of relax some things and get generalization. So the most obvious generalization of an inverse monoid is just regular monoids, where every element has an inverse, maybe not a unique one. These are important for all kinds of reasons, and these are also equivalent to similar kind of characterizations in terms of Green's relations and idempotence, which I'll gloss over again. You can take the requirement that idempotents commute. If idempotents commute, then the set of all idempotents form a subsemigroup. It'll be a commutative subsemigroup, so a semilattice. If you don't require that they commute, but just require that they form a subsemigroup, you get the class of orthodox monoids. Then we have restriction monoids, which are further generalizations. These came up in Richard Garner's talk. You can do everything with categories rather than monoids. So category elements in a category can have inverses and be regular and so on. And the two main generalizations that come up today are regular star monoids, which basically you take the identities I listed before and just throw away one of them, and Ehresmann monoids, which are very important generalizations of inverse monoids. So we'll get to these in a sec. So I'm going to motivate this by talking about these inverse monoids I mentioned. So monoids of partial bijections. Well, a partial bijection is just a bijection between subsets of a set. And we usually just denote these graphically like this. The elements of X are listed, and we just draw lines to say which point goes where. For a given X, the set of all such things forms an inverse monoid. It's called the symmetric inverse monoid. It plays the role of the symmetric group within inverse monoids. And well, to compose these things, you just do what you would if they were permutations. You join them up and then see what goes where. And in particular, we have an associative operation, and we've got an inverse, which is just the ordinary inversion of mappings, or in terms of the pictures, you just turn the picture upside down. And these are important because, as I said, they play the role of symmetric groups, meaning that any inverse monoid is basically an inverse monoid of partial bijections. Right, so there's a dual way to think about this, which is instead of looking at bijections between subsets, we think of bijections between quotient sets. So here we've got the set at the top decomposed into blocks. So we've got a partition of our set, and we've got a partition at the bottom, and we map the blocks bijectively to each other. This is called a block bijection. The dual symmetric inverse monoid consists of all these things. It forms an inverse monoid as well, and the composition is essentially the same. You just stack your graphs together and you see what's connected now. So now some of these blocks might get joined up in a fairly complicated way in the middle row, but you always end up with a block bijection back. You can turn a picture upside down to obtain an inversion operation, and there's a similar representation theorem due to Fitzgerald and Leach with respect to these things. So these give a dual approach to inverse monoids. And the next slide talks about partition monoids, and this is not the standard way to think of the partition monoid, but you can think of elements of the partition monoid as kind of partial block bijections. So we have two quotients of X, and we take a bijection from a subset of one of those quotients to a subset of another. So here is a block that just isn't in the domain of this thing. And yeah, like I said, the normal way to think of this is these things are set partitions of two copies of X. But we end up with a bipartition monoid, normally called the partition monoid. And the composition is basically the same. You stack these things together, you see what gets connected, and then you have a new one of these things. And this is not inverse. It's an example of a regular star monoid, which I won't go into all the details of, but it's almost like an inverse monoid where maybe the idempotents don't commute. Okay, and it turns out that this monoid, well, it's important for all kinds of reasons, and that's a whole separate talk. But it turns out that this is a nice example of an Ehresmann monoid. So, what is an Ehresmann monoid? This idea goes back to what's commonly called the York School of Semigroup theory. So, it was sort of started by John Fountain many decades ago and continued by his many students, two of which are Vicky Gould and Mark Lawson, pictured here. And John's observation was that a lot of the nice results about regular monoids or regular semigroups held not so much because of inverses existing, but because of corollaries of inverses existing. Similarly with inverse monoids, it was the uniqueness of inverses imply certain properties, and it's these properties that are so important and special. So the philosophy was to study monoids that maybe don't necessarily have inverses or unique inverses, but have some of these pleasant properties. And that led to the definition of many different families of semigroups. Probably the most famous ones are the abundant and ample ones, but there are so many generalizations like weakly left, E star, blah, 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 blah. Somehow these people have all of these in their heads. I definitely don't. But today's talk is about a particularly nice family called the Ehresmann monoids. And these came from this paper of Mark Lawson, Journal of Algebra in the early 90s. So to tell you what an Ehresmann monoid is, I'm going to look for some of these nice properties of inverse monoids to kind of inspire the definition. So take a monoid and two elements. Green's R relation is defined as follows. So X and Y are related if they generate the same principal right ideal of the monoid. Okay, another way to say this is that X is Y times something and Y is X times something. So you can get from X to Y by multiplying on the right. Now in a group, every element, every pair of elements are related like this. You have inverses, group inverses, so everything works. In general, this doesn't hold for every pair of elements. Then we've got the L relation, and we've got various other relations that we won't really need to discuss. But one property that's fairly apparent from this is that R is a left congruent. So if you have any pair of R-related elements, you can multiply them both on the left by anything, and you'll still be R-related. Basically, if X is YA, then of course CX is CYA as well. So I've got a left congruence. In the case that M is inverse, this R relation can be expressed equationally rather than by saying things are related if there exists something. You don't have to check everything. So it turns out X and Y are related if and only if this equation holds. Okay, so again, in groups, this always holds, but in inverse monoids, not necessarily. And there's another nice characterization of this in terms of the idempotents. It turns out X and Y are related if and only if they have the same set of left identities. So the left identity set of X is all the idempotents that act as a left identity for X. All right, an example of a left identity, well, obviously the identity element would belong to this set for every X, but X inverse does as well, because if you multiply X inverse by X, you just get X. Okay, also X turns out to be R related to X inverse. You can just multiply X inverse by X to get back to X. And it turns out that this is in fact the unique element of E that's R related to X. So every element is R related to a unique idempotent. And these observations lead to the definition of an Ehresmann monoid. Start with any monoid whatsoever. We start with any old semi-lattice of idempotents of M. So it could just be the identity element, or it could be all of the idempotencies if they happen to form a semilattice. And with respect to this set, we define these left identity sets. For any x, ELX is a set of left identities from this fixed semilattice. And we define a relation now RE by this rule here. So this was just the R relation if M was an inverse monoid, but we can still define this in terms of an arbitrary fixed semilattice of idempotents. And then we say M is left E Ehresmann if this is a left congruence and every element is related to exactly one element of E. There's a right Ehresmann definition that's just symmetrical, and we drop the left or right if it happens to be both of these things. So just keep in mind there's a semilattice floating around and some nice relations. All right, you can take, as I said before, any monoid with just the identity element. The left identities are always just the identity elements. Every pair of elements is related, or you can take an inverse monoid and everything reduces to the R relation. So why do we care about this? I'll kind of scroll through this fairly quickly. If we've got an Ehresmann monoid, then every element is RE related to a unique element of our semilattice and F related. So we've got some operations. We can write X plus for this E thing and X star for this F thing. And these guys behave a lot like a domain and codomain of X. You can write down a bunch of equations or identities that characterize the Ehresmann semigroups like so, but for the purposes of this slide, at least, we can use these things to define a category. The objects are the idempotents, so the fixed set of idempotents. And as I said, these things are just the domain and range operations. So for any pair of idempotents, we take all the elements whose plus is E and star is F. And it's kind of magic that when you compose these things, the domains and ranges match up appropriately. And Stein showed that if you're interested in the representation theory of your Ehresmann monoid, if you're lucky, that will have the same representation theory as this category. And you might think, okay, why do we want to turn a simple thing like a monoid into a complicated thing like a category? But this category is actually, in some sense, a simplification of the monoid. You take products that are kind of complicated and you just say that we can't even compose those things. So when you connect things, you don't worry if they don't match up. Okay, if they don't match up, you just throw them away. You only compose things that do match up, so you're just playing with a bunch of bijections. And this is kind of an extension of the fact that inverse monoids and groupoids are more or less the same thing. Stein also showed, for example, that the largest semi-simple image of a semigroup algebra is basically the semigroup algebra of a certain inverse submonoid, which in nice cases we can compute. So in the last couple of minutes, I'll try and explain what the Ehresmann structure is on the partition monoids. So partition monoids, remember, are these things, partial block bijections. We compose them by stacking them and then just seeing what ends up connected. An example of a partial block bijection would just be a block bijection, okay, where every block is mapped to another block. Or another one would be the partial bijections, where the blocks are just singletons. So partial bijections and block bijections are special cases, and that means that the two inverse monoids discussed before, the symmetric and the dual symmetric inverse monoids, are contained in here. So if you want an Ehresmann structure, you have to have a semilattice, and in particular, these two inverse monoids give us two semilattices. So the natural question is, can we just take the semilattices of either or both of these and do we get a nice Ehresmann structure? And the main result of the paper is that we do get an Ehresmann structure for the dual symmetric inverse monoid, and we don't get one for the ordinary symmetric inverse monoid. So it would have been nice if we got one for both, then we'd have this sort of, I don't know, dual approach. to this, but maybe it's even more intriguing that only one of these works. The proof of this involves, of course, learning about these RE-LE relations that is determined by kernels and co-kernels, which is basically the domain and codomain partitions. Once you have a structure like this, it just automatically gives you a whole bunch of interesting substructures. So H classes of idempotents in semigroups give you groups. HE classes in these things give you monoids, and the HE classes turn out to be isomorphic to symmetric inverse monoids. If you compute this thing that I very briefly touched upon before, the irregular elements, you get the dual symmetric inverse monoid on the same set, and so this relates the representation theory of partition monoids to those of dual symmetric inverse monoids. You can also find examples of restriction monoids here, and that led to the definition of some fairly interesting new diagram monoids, which I don't have time to talk about today, but maybe will another time. And of course, we use the theory to describe the categories that come up, and looked at representation theory of these things. And we had a chapter on relation monoids, which are natural examples of Ehresmann monoids. And there's a very interesting duality between subsets and quotients that arises here. So that was very interesting for us. We looked at some other things like Grau monoids and Rook partition monoids, but so this is sort of a vague summary of what's in the paper. So thank you very much, and if there are any questions, I'll be happy to try and answer them.